Imagine it's like 2 o'clock on a Tuesday afternoon.
Okay.
You're just sitting at your desk and you're staring at this completely blank design document. Your engineering manager just handed you the mandate to build the back end for the company's, massive new flagship feature.
Oh, that's always a fun moment. It's like
Yeah.
no pressure, right?
Right. And you know the requirements.
Yeah.
It needs to
Yeah.
be fast, it needs to scale globally, and it absolutely cannot go down.
Yeah.
And, 10 or 15 years ago, your first move would have been super obvious.
Yeah, you just provision a hefty server, install a standard relational database like MySQL or Postgres.
Exactly. Write some app logic and basically call it a day.
Yeah.
But today,
Yeah.
staring at that blank document, the landscape is it's totally different.
It's overwhelming, honestly.
It really is. It's just
Yeah.
a flood of architectural buzzwords. You've got team members pushing for NoSQL, someone else is insisting you need a data lake, and then there's terms getting thrown around like zero-disk architecture or event-driven microservices.
Right, and you're just sitting there like, how do I actually make a defensible choice here?
Exactly. Which brings us to the core mission of our deep dive today. We are going to provide a masterclass on the foundational engineering trade-offs in modern data systems.
Yeah, extracting the really critical insights from Chapter 1 of the second edition of Designing Data-Intensive Applications.
Right, because our goal is to bypass all the shiny vendor pitches and give you, the software engineer, the actual mental models you need to evaluate these technologies critically.
Because the paralysis you feel in front of that blank document is completely justified. The data ecosystem right now is incredibly noisy.
And the marketing departments for cloud providers,
Mm-hmm.
they obviously have a vested interest in convincing you that their specific tool is like a silver bullet.
Oh, absolutely. But making the wrong choice at the design phase, it doesn't just mean your code is a little messy later on.
What does it actually mean in practice?
Well, it leads to systems that silently corrupt user data, or, they rack up hundreds of thousands of dollars in unnecessary cloud bills, or they just crumble under the weight of a sudden traffic spike. You can't follow the hype.
You have to understand the fundamental physics of how these systems move and store data.
Exactly. But before we even get to evaluating the technologies, we have to define the constraints of the domain we're actually in.
Okay, let's set the boundaries.
Right. So the principles we're discussing today apply primarily to data-intensive applications. And that is a very specific categorization. It contrasts really sharply with compute-intensive applications.
I'm glad you brought that up because I think a lot of engineers conflate the two when they think about system performance.
Yeah, they just think slow means slow.
Right. Like if I'm building a highly complex physics engine for a video game or a massive video rendering pipeline, performance there is mostly gated by how fast the CPU can crunch numbers, right?
Exactly. In those compute-intensive scenarios, you are dealing with a CPU bottleneck. Your architectural challenges there revolve around parallelizing math operations.
Like spreading it across multiple threads or GPU cores.
Yeah. The data itself in those cases might be relatively small, like just a set of initial coordinates or vectors. But the transformations on that data are computationally super expensive.
Got it. So how does a data-intensive app differ?
Well, it operates under an entirely different set of constraints. The CPU is almost never the limiting factor.
Really? So what is the bottleneck then?
It's the sheer volume of the data and the complexity of how different pieces of data relate to each other, and critically, the velocity at which that data is changing.
Oh, okay.
In a data-intensive app, your bottlenecks are memory limits, disk I/O, and network bandwidth. You're basically constantly fighting to optimize how data gets written to a physical storage medium.
Right, like how quickly you can find one specific record among billions.
Exactly. And you're trying to figure out how to ensure that when 3 different users try to update the exact same record at the exact same millisecond, the system doesn't end up with, corrupted nonsensical state.
Which really highlights a massive shift in how we have to think about the front end versus the back end.
Oh, completely.
Because the front end, whether that's a mobile app or like a React web interface, it's mostly dealing with local state. It's managing the UI for just one single user.
Right. I mean, it has to handle complex rendering, sure, but it is fundamentally isolated from the rest of the world.
Whereas the back end is where you're managing concurrent state for millions of users simultaneously.
Yeah, and we manage that concurrency through a really specific architectural pattern that has become pretty much ubiquitous today.
Which is,
Stateless application servers backed by stateful data systems.
okay, let's unpack that for a second.
Sure. So your application code, like the Python, Go, or Java you write, to handle your actual business logic that typically lives on servers that treat every incoming HTTP request as a completely independent event.
So once the server finishes serving that request, it just forgets everything. It wipes its hands clean.
Exactly. It's stateless. Because if the app server holds onto a user's state in its local memory and that specific server crashes,
The user just loses all their data.
right. Or think about load balancing. If a load balancer routes that user's next request to a totally different app server, that new server has no idea who the user even is if the state was kept locally on the first server.
So to achieve scalability and resilience at the app layer, we just push all that complexity down into the infrastructure layer.
Exactly. The valuable, persistent truth of your application lives down in the databases, the distributed caches, the message queues. That is where the truly hard engineering challenges reside.
Okay, so let's get into those challenges. When we look at that storage layer, it seems like the first major fork in the road is understanding how the data is actually going to be used.
Yes. Data doesn't just exist in a vacuum. A database is ultimately just a tool serving humans, and the humans interacting with your application have entirely different objectives.
And recognizing those divergent objectives is basically step one of system design.
It really is. Historically, the failure to separate workloads has led to some of the most spectacular system outages in the tech industry.
So what's the primary division we need to make?
The biggest split is between operational systems and analytical systems.
Okay, I hear the terms OLTP and OLAP thrown around constantly. Let's start with the operational side. Online transaction processing.
Sure.
But I feel like the word transaction is a bit loaded here. People hear it and usually assume it means a financial transaction, like swiping a credit card.
Yeah, that terminology is definitely a relic of the 1970s and 80s, back when the primary use case for these systems actually was processing commercial and financial transactions.
Right, like bank mainframes.
Exactly. But in modern software engineering, an OLTP transaction is much, much broader. It basically refers to a group of interactive, low-latency reads and writes that are necessary for the user-facing application to just function.
So if I'm building like a social media platform and a user posts a new comment or likes a photo or updates their bio, those are all operational transactions.
Yes, absolutely. And from a mechanical perspective, the access pattern for those operations is highly specific.
How so?
Well, when a user updates their bio, the application doesn't need to scan the entire database. It just needs to find one specific user out of millions.
Oh, I see. It's doing a point query. The app essentially asks the database, hey, find me the record where user ID equals 8675309.
Precisely. And that lookup has to happen in milliseconds. To achieve that kind of speed, OLTP databases rely heavily on index structures, the most common being B trees.
Right, B trees. Let's touch on that quickly. It basically maintains an organized tree of keys, right?
Yeah, so it can traverse down to the exact physical location of that single user record on the hard drive.
Without having to scan or read anything else on the disk.
Exactly, it skips the bulk of the data. Furthermore, these operational queries are highly predictable.
Predictable because they are literally hard-coded into our application logic, right?
Yeah. Yes. The end user isn't typing raw SQL into a search bar on your website. They're just clicking a save button.
And that button triggers an API endpoint, which then executes a predefined SQL update statement.
Exactly. So the system is fundamentally optimized to handle a massive volume of these tiny, predefined, index-driven queries concurrently. It is the engine that keeps your live product running smoothly.
Okay, but the moment you have a successful product running on an OLTP system, the business side of the company is going to wake up and want to understand what the users are actually doing.
Oh, inevitably. And this is where online analytical processing, or OLAP, comes in.
So this is serving a completely different persona. We aren't serving the end user interacting with the app anymore.
No, now you're serving data scientists, business analysts, product managers.
And their access patterns are basically the polar opposite of the operational workloads we just talked about.
Completely. An analyst doesn't care about user ID 8675309 updating their bio. They want to understand broad macroeconomic trends within the platform.
A really great example from the source material is a supermarket.
Oh, yeah. That's a perfect way to visualize it.
Like the checkout register scanning a barcode and updating the inventory count for one single box of cereal. That's the operational system.
Right. Tiny, fast, specific.
But the analyst sitting at corporate headquarters wants to know something like, what is the correlation between baby food purchases and diaper purchases across all stores in the Midwest during the entire month of January?
Yeah. And to answer that question, the database cannot use a fast point query.
because it's not looking for one record.
Exactly. It has to scan millions of individual transaction records, filter them by date and location, extract the specific items purchased, and compute massive aggregations.
Grouping, summing, counting, all that heavy lifting.
Right. And unlike the operational side, these queries are entirely ad hoc. The analyst is writing custom SQL on the fly. The database has absolutely no way of predicting what they're going to ask next.
Okay, so this leads to a scenario that I think literally every junior engineer considers at some point in their career.
Oh, I know where you're going with this.
I mean, relational databases like Postgres are incredibly powerful. SQL is a universal language. If all my data is already sitting in my live operational Postgres database, why on earth would I spin up a whole separate system for analytics?
Why not just use the live DB?
Exactly. I could just give the analysts read-only access to the live production database. It saves me from managing complex data pipelines and spinning up new, expensive infrastructure.
Look, that instinct is incredibly common, and frankly, for a very small startup with like a few thousand users, you can usually get away with it for a little while. But as the data volume scales, running analytics on an operational system introduces severe resource contention. You have to think about what is actually happening at the hardware and operating system level when you execute a massive aggregation query.
Walk me through that. Let's say my analyst executes a query that requires scanning 50 million rows just to calculate last month's total revenue.
Okay, so when that query kicks off, the database engine has to pull those 50 million rows from the hard drive into memory.
Which takes time.
It doesn't just take time, it monopolizes the disk I/O bandwidth, and worse, it's going to flush the database's internal cache.
Oh, right. Evicting all the frequently accessed operational data just to make room for this massive historical scan.
Exactly. Plus, it will consume a massive number of CPU cycles to perform the actual aggregations and math.
And while all of that is happening on the server, my live users are trying to check out and buy things.
Yeah, and those checkout queries are suddenly starved for resources. The disk is busy serving the analyst, the CPU is pegged at 100%, and the cache data the live app needs is just gone.
So what used to be millisecond response times degrade into multiple seconds.
Transactions start timing out. The checkout registers in the supermarket effectively freeze. You have just caused a production outage, not because of a bug in your code, but because an internal reporting query competed with live traffic for the exact same physical resources.
Wow, okay. So the contention isn't just a minor slowdown. It's a fundamental physical conflict in how the hardware is being utilized.
Precisely. You just can't serve both masters efficiently on one node.
But even beyond performance, there's a structural problem today, right? Because in modern backends, we rarely have just one giant monolithic operational database anymore. If we follow a microservices architecture, we have dozens of them.
Right, which brings us to the issue of data silos. A modern engineering organization might have one database dedicated entirely to user authentication, then a completely separate database for billing, another one for inventory, another for shipping logistics.
We architect it that way so the billing team can deploy updates totally independently of the shipping team, right?
Exactly. Team autonomy.
And if the shipping database crashes, users can still log in and view their accounts.
It's fantastic for operational resilience, but it is an absolute nightmare for the analyst.
So,
Because the analyst needs to run a query that correlates a user's geographical location with their billing history and the shipping delays they experienced last week.
and that data lives in 3 completely isolated microservice databases.
Yes, and you simply cannot write a single SQL query that efficiently joins tables across 3 separate live databases over a network. It doesn't work.
This basically necessitates the classic data warehouse architecture.
Yes. The data warehouse emerged as the solution to both the resource contention problem and the data silo problem.
So what is it, fundamentally?
It is a separate, dedicated database system specifically designed and tuned for analytical queries.
Which means we need a way to actually get the data out of all those microservices and into the warehouse.
Mhm.
And this is where ETL comes in, right? Extract, transform, load.
Exactly. You set up automated pipelines. These pipelines periodically extract the latest data from the operational databases.
Usually overnight or in batches.
Right. Then you transform that data. You clean it up, resolve inconsistencies, and restructure it from an operational schema into an analytical schema.
Like a star snowflake schema, right?
Right.
Which is optimized for fast aggregations.
Yes. And finally, you load it into the central data warehouse.
I sometimes hear the acronym ELT as well. Extract, load, transform. Is there a big difference?
That's a more modern variation. With the massive compute power of modern cloud warehouses, things like Snowflake or BigQuery, it's often easier to just load the raw extracted data directly into the warehouse first.
And then do the transformations later.
Yeah, you use the warehouse's own massive computational engine to run the transformations via SQL views, but regardless of the order, ETL or ELT, the end result is the same.
You get a unified, structured, read-only environment where analysts can run massive ad hoc queries without ever touching or impacting the operational systems.
Exactly. You've solved the contention and the silos.
But the data landscape didn't stop evolving at the data warehouse. Warehouses are by nature highly structured. You have to define the schema before you load the data. You have to enforce rigid rows and columns.
And that rigidity led to serious friction with a new type of data consumer, the data scientist.
Because data scientists approach data completely differently than business analysts, right?
Very differently. An analyst is usually looking for specific business metrics, revenue, churn, active daily users. A data scientist is often trying to train machine learning models or discover completely hidden patterns through feature engineering.
And for machine learning, a clean, aggregated relational table isn't always the best input.
No, it often destroys the nuanced, noisy signals the data scientist is actually looking for. They don't just want neat rows and columns. They need the raw, unstructured, or semi-structured data.
What kind of data are we talking about?
They want the raw application event logs, the massive JSON payloads, the raw text of user reviews for natural language processing, or even image and audio files.
And this is what the source material refers to as the sushi principle, right?
Yes. The sushi principle.
The idea that raw data is often much better than pre-processed data.
It's an incredibly apt metaphor. If you pre-cook the data, if you transform it and aggregate it before storing it in a warehouse, you permanently limit what can be done with it later.
You can't unaggregate an average to find the original data points.
Exactly. By dumping the raw, untransformed data into a central repository, you preserve all its original fidelity. And this centralized repository for raw data is what we call the data lake.
And when we talk about storing data in a data lake, we aren't talking about SQL tables.
No.
We're talking about storing massive files in formats specifically designed for big data processing, things like Apache Parquet or Avro.
Right.
I really want to pause here because these formats are crucial, but rarely explained well to engineers just getting into this space. If I'm just saving raw data to a data lake, why not just dump everything as massive CSV files?
Well, I mean, you could, but it would be wildly inefficient for analytical workloads.
Why is that?
If you think about a traditional operational database or a standard CSV file, data is stored row by row.
Right.
So if you want to read all the data for one specific user, the hard drive just reads a continuous block of data containing that user's name, age, email, and address. That is a row-oriented format.
Which makes perfect sense for OLTP.
Right, because you need the whole user profile at once. But remember the analytical access pattern. An analyst might want to find the average age of all users.
Oh, I see. In a row-oriented format, like a CSV, the system has to read every single row from the disk, extract just the age field, and then basically discard the rest of the data in memory.
Exactly. It involves a massive amount of unnecessary disk I/O. You're pulling gigabytes of data into memory that you don't even need just to get the ages.
So a format like Parquet solves this by being column-oriented instead of row-oriented.
Exactly. In a columnar format like Parquet, all the values for a single column like age are stored contiguously on the disk together.
Oh, wow.
So when the analyst asks for the average age, the system only reads the age column from the disk. It completely ignores the names, emails, and addresses because they are physically stored somewhere else.
That must reduce disk I/O drastically.
Unbelievably so. Furthermore, because you are storing similar data types together, like a whole block of just integers for age, you can apply incredibly aggressive compression algorithms.
Which saves massive amounts of storage space and thus money.
Exactly.
And what about Avro? I see that mentioned a lot alongside Parquet.
So Avro is slightly different. It's actually still row-oriented, but it's highly optimized for schema evolution.
What does that mean in practice?
Well, when your application changes over time, you add or remove fields from your event logs, right?
Yeah, schemas are always changing.
Avro physically stores the schema alongside the data within the file itself. This makes it incredibly robust for data ingestion pipelines where the structure might shift from week to week.
Got it. So your data lake is filled with these highly optimized file formats, and data scientists can use distributed processing frameworks like Apache Spark to run machine learning algorithms directly against those raw files.
Exactly. They have all the raw fidelity they need.
Okay, so just to recap, we have OLTP for operational workloads, data warehouses for structured business analytics, and data lakes for raw machine learning and data science.
That's the holy trinity right now.
But I also see a ton of marketing around HTAP, hybrid transactional analytical processing. These are systems claiming to just do it all in one box.
Oh, HTTP, yeah.
They promise you can ditch the ETL pipelines entirely and run massive analytical aggregations directly on your live transactional data without the performance hit. How is that mechanically possible, given literally everything we just discussed about resource contention?
It's a great question. HTTP systems represent some of the absolute most cutting-edge database engineering happening today, but it is critical to look beneath the marketing claims.
Because you can't break the laws of physics.
Right. Scanning millions of rows will always require massive CPU and disk resources.
So how do they hide the contention from the live users?
They usually do it through really clever architectural tricks beneath a single unified interface. Often, an HTTP system is actually maintaining two completely separate storage engines under the hood automatically.
Wait, really?
Yeah. It maintains a row-oriented representation in memory for the fast operational point queries, and then it seamlessly replicates that exact same data in real time into a columnar format for the analytical queries.
Oh, that's wild. So when my app sends an insert statement, it goes to the row store. But when my analyst sends an aggregation query, the database engine acts like a smart router and directs the query to the columnar replica.
Precisely. It tries to offer the best of both worlds without the latency of a nightly ETL pipeline.
That seems incredibly useful.
These systems are incredibly valuable for highly specific use cases. Think of a credit card fraud detection system.
Okay.
You need to evaluate a live transaction in milliseconds. That's an operational requirement. But that evaluation requires analyzing the user's entire historical purchase history against a massive behavioral model.
Which is an analytical requirement.
Exactly. You need both. Instantly. HTAP shines there.
But for general enterprise architecture, should I just abandon my data lake and warehouse and migrate everything to an HTTP system?
Probably not. For most organizations, maintaining a physical separation between your microservices and your central analytical environment remains the most robust, scalable, and cost-effective practice.
Because HTTP is expensive.
It can be. And it often locks you into a highly specific vendor's ecosystem. Plus, the internal complexity of a system managing dual storage engines can introduce its own operational headaches when things go wrong.
Fair enough.
Yeah.
Let's assume we stick to the standard best practice then.
Yeah.
We have our microservices handling live traffic, we have ETL pipelines extracting that data, and we have warehouses and lakes storing it for analytics.
Right.
If you map that out on a whiteboard, it becomes very apparent that we are intentionally creating multiple copies of the exact same data,
Yeah.
spread across completely different systems.
Yes, you absolutely are.
As software engineers, the concept of duplicating data usually sets off massive alarm bells. We're taught from day one to normalize data to avoid inconsistencies.
Don't repeat yourself.
Right. So how do we manage all these copies without descending into complete architectural chaos?
That tension right there is one of the fundamental challenges of modern data architecture. To manage it safely, you have to adopt a very strict mental model regarding the hierarchy of your data.
What kind of hierarchy?
You have to explicitly define your systems of record, and you have to clearly distinguish them from your derived data systems.
Okay, let's define the system of record first. I hear this referred to as the source of truth.
Yes, the system of record is the authoritative origin point for a piece of data. When a real-world event occurs, a user registers an account, a sensor records a temperature reading, a payment is processed. The representation of that event is written first to the system of record.
And if there's ever a discrepancy between two databases in your infrastructure,
The system of record is right, by definition. End of discussion.
and to maintain that integrity, the data in the system of record is usually heavily normalized. Right?
Normalization is absolutely key here. You want to store a fact exactly once.
Why is that so crucial?
Because if a user's name is stored in 5 different tables and they get married and change their name, you have to find and update all 5 locations simultaneously.
And if one of those updates fails, maybe the network blips. You now have an inconsistency in your source of truth.
Exactly. A normalized system of records stores the name just once and references it via foreign keys everywhere else. This ensures that an update is a single atomic operation.
But the trade-off for that super clean, normalized structure is read performance, isn't it?
Always.
If I need to render a user dashboard that displays their profile, their recent orders, and their shipping status, I might have to execute a query that joins 6 different normalized tables together on the fly.
And performing massive multi-table joins on every single page load will absolutely destroy your application's latency.
Which brings us to the necessity of derived data systems.
Yes, derived data is any data that exists strictly as a result of taking existing data from another system and transforming it, copying it, or processing it for a specific read use case.
We used the analogy of a recording studio earlier, which I think is perfect.
Yeah, let's revisit that.
The system of record is like the original multi-track master tape. It is sacred. You lock it in a vault. You don't mess with it.
Right. And the derived data is the compressed MP3 file that you actually stream on your phone.
It's a highly accurate analogy because the defining characteristic of a derived data system is its reconstructability.
Yes. If your phone corrupts the MP3 file, you don't lose the song forever. You simply go back to the master tape in the vault and generate a brand new MP3.
So in software architecture, if a derived data system crashes, gets corrupted, or is wiped completely, it's just an inconvenience, not a catastrophe.
Exactly. You just write a script to reprocess the data from the system of record and you rebuild it. It might take some time, but no data is permanently lost.
So what are some common examples of derived data systems that engineers interact with on a daily basis?
Caching is easily the most common.
Like Redis or Memcached.
Yeah. When you use Redis to store the fully rendered HTML of a popular web page, or the pre-joined results of a really complex database query, that is derived data, you are intentionally trading memory capacity for speed.
And if the Redis cache server randomly reboots and loses everything in its RAM,
the application simply queries the slow system of record, rebuilds the response, and places it back in the cache.
search indexes are another huge one, right?
Oh, massive. If you're building an e-commerce site, you can't realistically run a SQL-like query across millions of product descriptions every single time a user searches for wireless headphones.
Because doing a full table scan on text is incredibly slow.
Painfully slow. So you use a specialized search engine like Elasticsearch.
How does that fit into the derived data model?
You take the raw product data from your system of record, extract the text, and run it through natural language analyzers.
Stemming words, removing stop words, that kind of thing.
Exactly. And you build an inverted index. The inverted index maps specific words directly back to the document IDs. This makes text search lightning fast.
But the Elasticsearch cluster itself is entirely derived.
100%. If the cluster fails, you just re-index the data from the main database.
Even materialized views inside a relational database fit this exact pattern.
Yeah, where you pre-compute a complex aggregation and store the result as a physical table.
And the data warehouse we discussed earlier, it is ultimately just a massive derived data system. It's a read-optimized copy of the operational systems.
Even the machine learning models trained by our data scientists are forms of derived data. The model's weights and biases are literally a mathematical derivation of the historical data stored in the lake.
What I find critical to understand here is that the label system of record or derived data is not like a sticker you read on the box when you download the software.
That's a vital distinction.
Postgres is not inherently a system of record. Redis is not inherently just a cache. It depends entirely on the flow of data that you design.
Right. You can absolutely use Redis as a system of record if you architect it that way.
Give me an example.
If you're building a real-time multiplayer game, and you use Redis to store the temporary volatile state of a player's coordinates on the map, and you don't save those coordinates anywhere else, then Redis is your authoritative source of truth for that data.
If Redis goes down, those coordinates are gone forever.
Exactly. The classification depends entirely on the data lineage.
And understanding that lineage is what prevents the architectural chaos. If you have redundant data, but you know exactly which system is the master and which systems are just the read-optimized replicas, you maintain total control.
It also gives you incredible flexibility. The text points out that data flow isn't always just a one-way street from operational to analytical. We are increasingly seeing a pattern called reverse ETL.
Reverse ETL. How does that work in practice?
Okay, imagine your data scientists train a sophisticated recommendation engine using the raw data in the data lake. That model predicts which products a user is most likely to buy next.
Which is great. But a model just sitting in a data lake doesn't help the live user experience on the website.
Right. You need to serve those recommendations to the user while they're browsing.
So you have to push the output of the analytical system back into the operational environment.
Exactly. You might deploy the trained model as a live microservice, Or you pre-compute all the recommendations overnight and load them into a fast operational database like Cassandra or Redis.
So the live web servers can query them in milliseconds.
Yeah. You are pushing derived analytical insights backward into the operational flow. But because you deeply understand the lineage, you know that if those recommendations get corrupted in Cassandra, you just rerun the model inference and push them again.
Okay, we've covered the theoretical flow of data. We know how to separate our workloads and how to manage the source of truth. Now we have to make a monumental physical decision.
Where does it all live?
Exactly. Where does this infrastructure actually physically reside?
Hmm.
The shift from physical data centers to the cloud is probably the most significant architectural tectonic shift of the last 2 decades.
It fundamentally altered not just how we deploy software, but how the database engines themselves are designed from the ground up.
But before we get to the architecture, we have to look at the business strategy. Because the decision of where to host your systems really comes down to the classic engineering dilemma, build versus buy.
It's all about allocating engineering bandwidth. And the core business rule outlined in the text is quite pragmatic.
Which is?
You should only build things in-house if they represent a core competitive advantage for your specific business. Everything else should be outsourced.
I feel like engineers, by our very nature, have a massive bias toward building things ourselves. We like control. We like compiling from source.
We do. But if you're building a streaming service like Netflix, your custom video encoding algorithms and your global content delivery network, those are your competitive advantages.
But managing the underlying hardware for the database that just stores user login credentials.
That doesn't differentiate you from your competitors at all, so you outsource that undifferentiated heavy lifting to a cloud provider.
But outsourcing to the cloud isn't a binary choice. It's a spectrum.
Definitely. On the far left, you have total control. You own the physical data center, you rack the servers, you plug in the network cables, you configure the cooling, and you install bare metal databases.
Which very few companies do anymore.
Right. Moving one step to the right, you have infrastructure as a service, or IaaS. This is where you're renting virtual machines from AWS or Google Cloud.
You aren't racking physical servers anymore, but you are still logging into a Linux terminal, the SSH, installing Postgres, configuring the hard drives, managing the backup cron jobs, and applying security patches.
Right, you are basically self-hosting, just on rented hardware.
And on the far right of the spectrum, you have fully managed cloud services and SaaS.
Here, you don't even have access to the underlying operating system.
Right.
You use a service like Amazon DynamoDB or a managed MongoDB Atlas cluster.
The provider handles the hardware, the OS, the database version upgrades, the backups, and the scaling.
You literally just interact with an API endpoint.
But this transition to the cloud didn't just change who manages the servers. It sparked the creation of an entirely new category of databases. We use the phrase cloud native all the time.
It's a massive buzzword.
But I think it's important to clarify that simply taking a 15-year-old database technology, installing it on a cloud VM, and running it on AWS doesn't magically make it cloud native.
Not at all. Traditional relational databases were architected with a very specific physical assumption in mind.
What assumption?
They assumed that the CPU processing the query and the hard drive storing the data were housed in the exact same physical machine, connected by a high-speed motherboard bus.
Right, the data is local.
True cloud-native data systems like Snowflake, Google BigQuery, or Amazon Aurora, they challenge that fundamental physical assumption. They are built on a paradigm called the decoupling of compute and storage.
Walk me through the actual mechanics of that decoupling.
In a decoupled architecture, the compute nodes the servers that actually parse the SQL queries, build the execution plans, and perform the aggregations. They do not hold the permanent data on their local drives.
Where does it go?
The permanent data is stored entirely separately on specialized cloud storage networks.
And usually that specialized storage is object storage, like Amazon S3 or Google Cloud Storage. Now, this is where I start to get really skeptical.
I don't blame you.
If I'm an engineer, I think of S3 as a place to store user profile pictures or massive video files or like nightly database backups. It's essentially a web API over HTTP.
Right.
The idea of using an HTTP-based object store as the foundational storage layer for a high-performance database seems kind of insane. S3 is not known for low latency.
You're identifying the exact physical limitations of the medium. Object storage has a much, much higher latency than a locally attached SSD. And cloud providers charge you for every single API, call every PUT and JT request.
So if a cloud-native database issued an HTTP request to S3 every time a single user updated their profile,
the latency would be measured in hundreds of milliseconds per query, and the API billing would bankrupt the company in a week.
yet we have systems doing exactly this. The text describes the extreme end of this spectrum as zero-disk architecture, or ZDA.
ZDA pushes decoupling to its absolute limit. In a zero-disk architecture, the compute nodes have literally zero persistent state. They might have massive amounts of RAM or local ultra-fast NVMe solid-state drives.
Let's just define NVMe really briefly for the listeners.
Sure, non-volatile memory express. It's a protocol designed to connect solid-state drives directly to the CPU via the PCIe bus, totally bypassing older, slower storage controllers.
So it provides incredibly fast, low-latency access to data.
Extremely fast.
Okay, so the compute nodes have RAM and these blazing fast NVMe drives, but you're saying they don't use them for permanent storage.
Exactly. The local NVMe drives are used strictly as a massive temporary cache. If a compute node loses power or crashes, you lose nothing permanent.
So how does it recover?
The system just spins up a new stateless node. It pulls the data it needs from S3 to warm up its NVMe cache, and it resumes processing. S3 provides the ultimate durability.
But we still haven't solved the latency problem.
Mm.
How do they write to S3 without incurring that massive HTTP overhead and API cost?
They solve it by completely changing the write path. Is zero-disk architecture almost never writes a single row directly to object storage. They rely heavily on batching.
So they just hold the incoming writes in memory.
Yes. The compute node receives thousands of insert and update requests and buffers them in its local memory.
Okay.
Once it has accumulated a large enough chunk of data, say several megabytes, it compresses it and writes that entire block to S3 in a single API call.
Oh, I see. This amortizes the network latency and the API cost over thousands of individual operations.
Exactly.
But hold on, let's think about failure scenarios. If I send an update to the database and the database tells me success, but it's really just holding my update in a memory buffer waiting to build a batch, what happens if the server crashes before it flushes that batch to S3? My data's just gone. That violates durability, which is like the cardinal rule of databases.
Which is exactly why there is a crucial intermediate step. To guarantee durability without waiting for the slow S3 batch write, these systems utilize a separate, specialized storage tier purely for the write-ahead log, or WAL.
How does the WAL function mechanically in this setup?
A write-ahead log is basically just an append-only file. It doesn't organize data into complex index trees. It simply records the raw changes sequentially as they happen.
Like, user A changed their name to X, user B updated their balance to Y.
Right, and writing sequentially is computationally very cheap and very fast because the disk head just writes continuously without seeking.
So when a write comes in, the database quickly appends it to the WAL.
Yes, and crucially, this WAL is typically stored on highly available, extremely low latency cloud storage, something like Amazon EBS, or a specialized distributed logging service.
Ah, okay. I see the whole picture now. So the flow is the write request hits the compute node. The compute node immediately writes the change to the fast, low-latency WAL.
Right.
Once the WAL acknowledges the write is safe, the database tells the end user, success. The data is now safe against a crash.
Because if it crashes, it just replays the WAL.
Right. Meanwhile, the compute node is still holding the actual data in memory, waiting to build up a massive batch. And eventually, it writes that massive compressed block to S3 asynchronously in the background.
That is the exact mechanism. It's a multi-tiered approach. Fast, small writes to the WAL for safety, massive batched writes to S3 for cheap, limitless, decoupled storage.
That completely hides the latency of object storage from the application layer.
Exactly, while allowing you to scale your compute nodes totally independently from your storage footprint. If you need more read capacity, just spin up more stateless compute nodes. They all read from the same S3 bucket. It is a masterpiece of distributed engineering.
It really is brilliant. But this heavy reliance on managed cloud infrastructure brings up a cultural issue within engineering teams that we need to talk about.
The NewOps myth.
Yes, there's this persistent myth that moving to the cloud and adopting managed services means NewOps. The idea that operational tasks just vanish and developers can focus purely on product features.
It is a really dangerous fallacy. The cloud does not eliminate operations. It merely translates them into a completely different domain.
You no longer have a physical operations team running cables and replacing failed hard drives in a freezing cold server room.
No, but the complexity of managing the system hasn't disappeared, it's just shifted.
Let's talk about how that shift manifests.
Okay.
Capacity planning is a great example. In the old days, you had to forecast your user growth 3 years in advance, right?
Yeah, you'd buy the physical servers and wait 3 months for them to be delivered and installed.
Over-provisioning was the norm because running out of capacity meant your business literally stopped. But in the cloud, capacity is infinite and instantaneous. You can spin up 100 servers with a single API call.
But that instantaneous scalability introduces a new, highly dangerous hazard. Capacity planning transforms into financial planning, often called FinOps.
Because you pay for exactly what you use.
Right. Think about it. In a physical data center, a poorly optimized SQL query that scans an entire massive table just runs slowly.
It's annoying, but it doesn't cost extra money.
But in a cloud-native architecture like BigQuery, where you pay per byte processed, that same poorly optimized query can cost you $1,000 every single time it executes.
I have absolutely seen the horror stories on Twitter of startups nearly bankrupting themselves because a junior engineer accidentally put a massive cloud query inside a while loop.
You have to deeply understand the billing mechanics of your architecture. It is a core engineering responsibility now. And you also have to manage the hidden operational constraints imposed by the cloud providers themselves.
You're talking about quotas.
Yes, the cloud might have infinite capacity globally, but AWS or Google do not expose all of it to you by default. They enforce strict service quotas to protect their infrastructure from runaway scripts and to manage their own hardware pools.
So you might have a hard limit of, say, 100 virtual CPUs in a specific geographic region.
Exactly. Which means if your marketing team launches a wildly successful campaign and your auto-scaling groups trigger to handle the massive traffic spike,
You might suddenly hit that invisible quota wall.
and the cloud provider will simply refuse to provision new nodes, your app goes down just as decisively as if a physical server lost power.
All because nobody filed a support ticket 2 days ago to request a quota increase.
Exactly. And beyond FinOps and quotas, the operational burden of security changes entirely in the cloud.
How so?
In a physical data center, security often relied heavily on the physical perimeter, firewalls at the network edge. Once you were inside the network, things were relatively trusted. But in a cloud-native environment, your architecture is composed of dozens of managed services communicating over the internet.
Which requires complex identity and access management, or IAM.
Managing IAM policies is a massive operational discipline. You have to define granular permissions specifying exactly which microservice is allowed to read from which specific S3 bucket and which service can trigger which Lambda function.
A misconfigured IAM policy can either break your application by denying access,
Or cause a catastrophic data breach by exposing internal services to the public internet. So CloudOps is a very real, very demanding full-time job.
Okay, let's pivot to the final major architectural threshold discussed in the text. Regardless of whether you build your own data center or embrace cloud-native decoupling, if your application is successful and continues to grow, you will inevitably hit the physical limits of a single machine.
Oh,
Because the largest, most expensive server money can buy still has a hard ceiling on its CPU, its memory, and its network bandwidth.
right. And when you cross that threshold, you have to move from a single node system to a distributed system. And this is a profound conceptual shift for an engineer.
And as the source material makes very, very clear, it is a shift that brings immense power, but also an incredible amount of pain.
You are adopting what is fundamentally known as a shared nothing architecture. You are taking a single cohesive system and breaking it apart, spreading it across multiple independent computers connected only by a network cable.
Before we talk about the pain, let's justify the decision. Why do we voluntarily take on the immense complexity of a distributed system?
There are three primary drivers. We've touched on the first one. Scalability. When your read or write volume exceeds a single machine, horizontal scaling is literally your only option. You add more nodes to the cluster to distribute the load.
The second is fault tolerance, which is really about high availability.
Right. If your entire database lives on a single machine, that machine is a single point of failure. If the motherboard fries, your application is completely down until you can restore from a backup.
But in a distributed system,
You replicate the data across multiple nodes. If one node catches fire, the system automatically redirects queries to the surviving nodes, providing a seamless experience for the user.
and the third driver is latency, which is ultimately a fight against the speed of light.
Exactly. If you host a single database server in Virginia and a user in Tokyo attempts to interact with it, the electrical signals literally have to travel across the globe.
That physical distance introduces unavoidable network latency.
Right. By distributing the system, you can deploy database replicas in geographic regions close to your users, ensuring low latency interactions worldwide.
Okay, those are powerful incentives. Scalability, resilience, and speed. But you mentioned this requires a conceptual shift. What makes building and maintaining distributed systems so uniquely painful?
The pain stems from the brutal reality of network communication. To understand this, you have to contrast it with how a single computer works. On a single machine, hardware is generally deterministic and binary in its failure modes.
What do you mean by binary?
If your RAM module fails, the operating system kernel panics and the machine halts. It is a total clean failure.
The classic blue screen of death. It's annoying, but it's unambiguous. You know the machine is dead.
But in a distributed system, you are dealing with dozens or hundreds of independent machines communicating over an unreliable network. This introduces the nightmare concept of partial failures.
Explain how a partial failure manifests.
Okay, imagine your application server needs to fetch data from a database node. It sends a request packet over the network. In a distributed system, any number of subtle things can go wrong.
Like what?
The network switch between the two servers might be overloaded and simply drop the packet.
So the database never even gets it.
Right. Or the database server might receive the request, but its hard drive is suddenly performing at 10% of its normal speed because of a weird hardware degradation.
So it's not dead, just incredibly slow.
Exactly. Or the database processes the request perfectly and sends the response back, but the response packet gets lost in the network on the return trip.
And because it's a shared nothing architecture, my application server has no omniscient view of what actually happened. It just knows it sent a message and hasn't heard back yet.
That's the core issue. It doesn't know if the database is dead, if it's just slow, or if the network is dropping packets. The application server basically has to guess, usually by implementing a timeout.
I'll wait 5 seconds, and if I don't hear back, I'll assume it failed.
But what if the database was just processing a heavy load and needed 6 seconds? You've timed out and recorded an error, but the database actually completed the operation and changed the data.
Oh man, that creates massive consistency problems.
And the worst part is that the rest of the system keeps running. A single degraded node or a flaky network switch can introduce subtle errors and massive latency spikes across the entire architecture, while traditional monitoring tools might report that all servers are theoretically up.
It's like having 1,000 tiny invisible paper cuts in your infrastructure. How does an engineer even debug something like that? I mean, if I have a monolithic application on my laptop and I find a bug, I can attach a debugger, pause the execution, and step through the code line by line.
That traditional debugging paradigm is entirely useless in a distributed system. You cannot attach a debugger to a user request that hops across an API gateway, triggers 3 separate microservices written in different languages, and queries 2 different databases.
So what is the alternative? We can't just fly blind.
The alternative is embracing comprehensive observability. You have to design the system from day one to constantly emit data about its own internal state.
We hear a lot about monitoring versus observability. Are they the same thing?
Not at all. Monitoring is basic. Is the CPU usage below 80%? Is the server responding to pings? Monitoring tells you if a system is broken.
And observability.
Observability is much deeper. It requires heavily instrumenting your code so you can ask arbitrary questions about why the system is behaving a certain way.
And the cornerstone of distributed observability is distributed tracing, right?
Yes. Tools like OpenTelemetry, Zipkin, or Jaeger are essential here.
Let's look at the mechanics of tracing. How does it actually track a request?
Okay, when an HTTP request from a user hits your outer API gateway, the gateway generates a unique cryptographic ID, a trace ID.
And then that trace ID is injected into the HTTP headers of every single subsequent network call that stems from that original request.
Exactly. When the API gateway calls the user microservice, it passes the trace ID. When the user microservice sends a gRPC call to the billing microservice, it passes the trace ID. When the billing service queries the database, it logs the trace ID.
Just to clarify for the listeners, gRPC is Google Remote Procedure Call. It's a high-performance framework that microservices often use to communicate with each other, right? Using protocol buffers instead of standard JSON.
Correct. It's much faster, but it's still a network call susceptible to partial failure.
Right.
So as each service handles its piece of the request, it records a span. A span is just a time-stamped log of exactly when it started its work and when it finished, tagged with that overarching trace ID. It sends these spans asynchronously to a central tracing server.
So when a user files a support ticket saying, the checkout process took 12 seconds instead of 1 second, you don't have to guess where the slowdown was.
No guessing required.
Mhm.
You search the tracing system for that specific user's trace ID. The system reconstructs the entire journey and generates a waterfall chart.
Oh, those are so satisfying to look at.
They really are. You can see precisely that the API gateway took 5 milliseconds, the user service took 10 milliseconds, but the gRPC call to the billing service hung for 11.9 seconds before timing out and retrying.
You've instantly isolated the partial failure.
Exactly. Without distributed tracing, finding that bottleneck in an architecture with 50 microservices is practically impossible.
This immense complexity of managing distributed microservices raises a really interesting philosophical point from the source material.
Oh, about supercomputers.
Yes. When we architect these cloud systems, with Kubernetes orchestrating thousands of independent containers over untrusted networks, we accept a massive amount of overhead just to handle failure gracefully. But compare that to how actual supercomputers are built.
It's a brilliant contrast that highlights the assumptions we bake into our web architectures. Supercomputers are essentially massive distributed systems too, but they are built for entirely different workloads.
They're built for massive batch processing, like running complex climate simulations or molecular dynamics models that take weeks to compute.
Right, and because they control the entire environment, supercomputers assume a highly trusted, incredibly reliable network. They often use specialized networking hardware and protocols like RDMA, remote direct memory access.
Which basically allows one server to read or write data directly into the RAM of another server, completely bypassing the operating system's network stack.
It is incredibly fast, but the most significant difference is how they handle failure. In a cloud-native microservice architecture, if a node fails, we expect the system to route around it dynamically so the end user never sees an error. We design for continuous availability.
But a supercomputer takes the exact opposite approach.
Yes. If a single node in a 10,000-node supercomputer cluster experiences a hardware failure during a climate simulation, the system does not try to dynamically reroute the calculation.
Why not? That seems fragile.
Because the entire simulation is a single, tightly coupled batch job. If one piece fails, the math for all the subsequent steps will be wrong. So the entire massive cluster stops.
It just halts.
It halts completely. The administrators physically replace the failed hardware. Then the system reboots and resumes the calculation from the last saved state, known as a checkpoint.
It's literally a stop-the-world approach to failure.
Which is perfectly acceptable for a scientific batch job that runs for a month. But you cannot apply that architecture to a global e-commerce platform.
Right. You cannot pause the entire website for 20 minutes.
Right.
Because one container in the inventory service ran out of memory.
Which brings us full circle. The systems we build in the cloud have to operate in hostile, multi-tenant environments with untrusted networks, and they must guarantee uninterrupted service to users despite the constant reality of partial failures.
It is a profoundly difficult engineering challenge.
It really is, which is why that original blank design document we talked about is so intimidating.
So as we wrap up this masterclass, how do we synthesize all of this? If you were the engineer tasked with designing this new backend today, what are the core takeaways?
The overarching lesson is that designing data-intensive applications is never about finding the perfect database.
There are no silver bullets in system architecture.
None. Every decision is an explicit trade-off. You have to master the workload trade-off first. Do you need a B-tree-based OLTP system optimized for millisecond point queries to serve live users? Or do you need a columnar OLAP database optimized for massive aggregations to serve business analysts?
And you must define your data lineage. You have to clearly identify your normalized system of record and consciously design your derived data systems.
Right. Your caches, search indexes, materialized views, you have to accept the complexity of keeping them in sync in exchange for the read performance you get.
You also have to evaluate the physical infrastructure. Will you manage the VMs yourself? Or will you embrace the cloud-native decoupling of storage and compute, relying on the complex orchestration of object storage and write-ahead logs?
And finally, you must confront the reality of distributed computing. You must weigh the essential benefits of scalability and fault tolerance against the immense operational burden of managing partial failures and implementing rigorous distributed observability.
Every choice has a cost, whether it's latency, financial expense, or operational complexity.
And the job of the software engineer isn't to magically avoid the cost. It's to choose the specific cost that aligns with the business requirements of the product you are building.
That is the absolute essence of software architecture.
It really is.
And that brings us to a final, slightly philosophical thought to close on, inspired by the broader themes of the text. As engineers, we spend our days obsessing over immediate performance. We run load tests to shave 5 milliseconds off a database query.
We argue over indexing strategies and caching layers for days.
We are constantly optimizing for today's peak load. But software is a unique medium. It doesn't suffer from material fatigue. A physical bridge will eventually rust and crumble no matter how well it was built.
But code does not rust.
Exactly. But despite not rusting, if a system you design today is successful and valuable, it will inevitably survive long enough to become a dreaded legacy system.
Oh, that is a guarantee.
10 years from now, another engineer is going to be staring at your code, deeply frustrated by the architectural choices you made today, wishing they could tear it down. The business requirements will change, the hardware landscape will shift, the cloud providers will release new paradigms.
The architecture that is perfectly optimized for today will eventually become tomorrow's bottleneck.
So perhaps instead of solely optimizing for raw throughput or minimal storage costs, there is a higher, more valuable metric we should be aiming for when we architect these data systems.
For the metric of evolvability.
Evolvability. It is the architectural humility to realize that whatever you build will eventually need to be replaced.
Designing an evolvable system means establishing clean boundaries, decoupling components, and isolating state.
So that 5 years from now, you or the engineers who follow you can completely dismantle, rewrite, and replace massive sections of the data infrastructure without the end users ever noticing a disruption.
It is designing a system that gracefully accepts its own eventual obsolescence.
Something to ponder the next time you open up that blank design document and write the very first line.